Hello guys, welcome to homework 18B. Sorry, I didn't know about this homework earlier, so I'm just doing it right now, and I'll send the link to you guys so you can watch. I'll share this right away so you guys can catch up before the deadline. In case you hear the TV background, my kids are here, you might hear their voices. Okay, I'm babysitting today at the same time doing this video, so pardon me. The first problem, as you guys can see here, let me make this bigger. It says 3-point charges, some positive and some negative, are fixed to the corners of the same square in various ways. As the drawings show, each charge, no matter what its algebraic sign, has the same magnitude. In which arrangement, if any, does the net electric field at the center of the square have the greatest magnitude? So the correct answer is the magnitude of the electric field at the center, the net, the total, is the same. So let's tell you why it's the same. So when you are finding the electric field, also known as electric field intensity, also known as electric field strength, is the same thing. Electric field by itself, or electric field intensity, or electric field strength. It means at the point you are finding that electric field, assume there is a positive charge and then see what happens. So we're looking for the electric field at the center of the square. So let's place a positive charge there. So this guy will repel it, this guy will repel it. They are of equal magnitude, so those two will cancel out. So the only one affecting it is this guy here, repelling it towards this side. So we have one going that way. So now they want only the magnitude. The directions might be different in all four, but the magnitude is the same. So that's what we're trying to prove. So I only have one charge pushing it the other way. Electric field due to this guy, these two will also repel, they'll cancel out. I have one charge attracting the positive charge to the other way from the center. Then for this guy, the C part, I have it at the center. This guy is repelling it, and these two are attracting it, they cancel out. So we have two of the same charge opposite the corners, in opposite corners, and they both cancel out. So only one charge affecting the center at all points, and they have the same magnitude, so the same electric field strength, the magnitude. The directions are different. So the direction for this one will be going that way, east, south. Then this one will be going up that way, north, west. Then this one will be going down, east, south. This one will be going up, northwest. So depending if it's positive or negative, that's left. But these two contributions cancel for each of the square. That's why you have the same magnitude here. Okay. Next, this was focused on concept, question 15. Now let's look at question 15. A 1.4 microcoulomb charge is placed between the plates of a parallel plate capacitor. The charge experiences a force of this. What is the magnitude of sigma, the surface charge density? So electric field is sigma over epsilon naught, which is electric field is force per unit charge. So we have the force, we have the charge, so we can get our electric field. So sigma over epsilon naught equals force over charge. Force is 0.2 newtons, charge is 1.4 microcoulomb. 1.4 times 10 to the power negative 6. So when I solve this, it gives me sigma over epsilon naught. I know my epsilon naught is 8.85 times 10 to the power negative 12. And then I just do the math, I get sigma to be this coulomb per meter squared. Okay. So these are two similar formulas for electric field. Sigma of epsilon naught is electric field, force per unit charge is electric field, and that's what I use to simplify this, to find sigma. I know force, I know charge, I know epsilon naught, I find sigma directly. Okay. Next, focus on concept, question 16. The drawing shows an electric field line. What are the directions of electric fields at point A, B, and C? So at point A, you're going to see the electric field is always tangential, tangent. At point A, the tangent is going down, so it's going to be due south. At point B, the tangent is going that way, so it's going to be southeast. And then at point C, the tangent is flat this way, so it's going to be due east. So it's always tangential line. So the direction of an electric field is the direction that is tangential to the field line. Okay. The drawing shows some electric field lines. For the points indicated, rank the magnitude of the electric field in descending order, largest first. So where the field lines are more compact, tight together, they have more field strength. So B is the highest, followed by C, followed by A. So B has more lines close to each other, followed by C, less close. A has the least close to each other. So B, C, A is the correct arrangement in descending order. Come on, DD, sorry. sorry. Okay, then the next one here, chapter 18, problem 31, an electric field of 410,000 Newton per coulomb points due west at a certain spot. What is the magnitude of the force that acts on a charge that is negative? So we know electric field is force per unit charge. So force is electric field times charge. So when you multiply that, we get this force. But because the force is negative, then the direction will be opposite that of the electric field. The electric field was due west, so the force will be acting due east. Okay. Another way to understand this problem is electric field is direction of positive charge. So direction of negative charge, electric field will be opposite that of positive charge. So if an electric field is already pointing due west, it means that's where a positive charge will go. So a negative charge will go the opposite direction. That's another way to see through the problem. Hey, Didi, stop eating my keys. Oh. Okay. So we have 3 more problems and we're done. The next one, chapter 18, problem 36. The membrane surrounding a living cell consists of an inner and outer wall that are separated by a small space. Assume that the membrane acts like a parallel plate capacitor in which the effective charge density is given to be this. And then we are asked to find the electric field. So electric field is sigma over epsilon naught. We have sigma, the charge density given, the surface charge density, just divided by epsilon naught, which is a constant. Permittivity of free space, 8.85 times 10 to the power negative 12. And that gives us our answer. And then we want a force. Force is charge times electric field. And the charge they are saying right there, it's a proton, right? On a potassium ion, sorry, a potassium ion, which the charge is given to be the charge of a proton. So an ion, it's ionized to a positive charge of a proton. So we're going to use that positive charge times the electric field we just got. That gives us our force. And that's it. Okay. Next problem. 4 charges with equal magnitude of this are placed at the corners of a rectangle. The length of the sides of the rectangles are this and that. So find the magnitude of electric field at the center. So they have 2 situations. This is the first situation we're going to solve, and then we'll do the second situation. The first situation has plus, minus, plus, plus. The second situation has minus, minus, plus, plus. So be careful. Remember what I told you about finding electric field. Assume there is a positive charge at the point you want the electric field. We want the electric field at the center. We assume there's a positive charge there. This will repel, this will repel, this will repel. This 1 and 3 repelling will cancel out because they are repelling in the same opposite direction. They'll cancel out with equal magnitude. So this is repelling the positive charge at the center. The minus here is attracting the positive charge at the center. So those 2 will combine together. So, but I need this distance from this charge to the center and this distance to that. So they have the same distances to the center. I don't know that distance. I only know the sides. So I'm going to calculate D using Pythagoras. This side square plus this side square root, and I divide D by 2. That becomes my R, the distance of each charge from the center. That's what I need to put in. Take Q times K over R squared. So they have the same charge. So the electric field at the center for this first one is just going to be twice electric field due to 4 or 2, any one of them, just multiply by 2 because they combine together in that direction. So when I combine those 2 together, I get this. So that is my electric field in that direction. So that's the magnitude of the electric field combined together in that direction. Then for the second part, you're going to see why these arrows are like this, because this is negative attracting a positive charge. Assume there's a positive charge in the center, it's going to attract. This is positive repel, so both will combine in that direction. This will repel, this will attract, both will combine in that direction. So I have 2 of them combining like that in that direction. So I have to find this guy and find that guy. But each of these is the same as what I got before. So E24 is the same as E24 here. E13 has magnitude of E24. So I have both of those. I just need to get the Y component. The X component are going to cancel out when they go opposite direction because they are the same magnitude. So the X component this way will cancel. I only need the Y component. So let me go to the next slide. So they are the same magnitude. So the X component cancel out. Then the Y component is getting the Y twice of each sine angle theta. I have to find that angle theta using this 7.14 divided by D, which I have. And then from there I can get the the angle here, theta, okay? So I'm using sine of theta. So my theta is this angle here, theta. So opposite over hypotenuse, sine theta is 7.14 over hypotenuse d. So this is the same theta right here. So sine theta will go to the y and cosine theta will go to x, but the x is cancelled out. So we don't need to work any x components. So that's how you get this sine theta here. And you combine the two times one of the forces, 71.9, then sine theta. 2 times 71.9, and then sine theta is 0.858. Okay. And then the last problem here says a small drop of water is suspended motionless in air by a uniform electric field that is directed upward and has a magnitude of 9910 Newton per coulomb. The mass of the water drop is this. How many excess electrons or protons reside in the drop? So it's suspended. So that suspension gives us an idea that it's in equilibrium. And being in equilibrium means the mass of that water drop, is that okay? Is equal to the electric force. I mean, the weight of the water drop balances the electric force holding it in the air. So mg is the weight equals electric force is charge times electric field intensity. So from there we can get the charge mg over electric field. And then from there we know the electric field is given, we know the mass, we know g, we can get our charge. Then divide by the number of protons, the charge of a proton. The charge of a proton is 1.6 times 10 to the minus 19 to tell us how many protons are inside this charge. Then we get that. That is the final answer. I hope this helps. See you guys next time. Thank you and sorry for bringing this late. Have a good one, guys.